Okay, so we know that from the previous video that the center of mass, written as a vector, comes from all of the little masses at their position so all the way up to, let's say, mn Rn, all over the total mass. Well, we could rewrite that by multiplying both sides by the total mass, and we get mass times the position of the center of mass comes from m1 R1 plus m2 R2 plus all the way up to mn Rn. So what happens if we take the derivative of both sides? Well, if we take the derivative of all these positions, we get mass times the velocity of the center of mass equals all of the individual masses times their individual velocities. And this is a hugely important value right there, but we're going to come back to it. But just maybe in your notes put a little asterisk and say this is something of interest. But let's say, okay, let's take the derivative one more time. So if we take the derivative again, we get mass times the acceleration of the center of mass. Interesting. Equals all of the individual masses times their accelerations. And this should look very familiar. And what we get here is that the net force on a system equals the mass times the acceleration of the center of mass. And this is a really important idea. So even if we have like a bunch of different particles all moving, we can treat the center of mass as being one particle. Let's think of this. We've got two interesting applications of this. First one, so imagine purely frictionless surface. And we've got one person over here, another person over here, and just for interesting sake, let's say that this person has mass 2m and this person has mass m. And they are holding a rope. Okay, so first of all, well, where's the center of mass? The center of mass we could find out pretty quickly. You know, if we call this the origin, the center of mass would be, let's call this a distance of, let's say 5 meters. So the center of mass would be 2m times 0 plus m times 5 all over the total mass, which is 3m. So we get that the center of mass is occurring at the point 5/3. And just as far as like, does that make sense? Of course that makes sense, because the halfway point would be, you know, at 2.5 meters, and we're to the left of that, somewhere in here. And it makes sense that we're to the left of the halfway point because to the left has a greater mass than to the right. Okay, so here's our center of mass, and let's just notate that with, you know, a little box. So we could treat, you know, the two different people as just one person at this point, you know, right in here, and the center of mass is right there, and we could treat the system as having a mass of 3m. So if all of a sudden they start pulling on this rope, what's going to happen is both are going to start moving toward one another. However, if we think about this as being a closed system, so if we're looking at kind of the system right here, those forces are internal forces. There is no net external force. So that the net force on the system equals 0, which means that the acceleration of the center of mass must equal 0. So the center of mass will stay. Center of mass remains stationary. So the question is, where do these two meet? Well, since the center of mass must remain stationary, the two are going to meet right at the center of mass. Pretty interesting. Let's look at another kind of interesting idea. Let's imagine you've got a model rocket. And your model rocket, you're going to launch from the ground. And it goes up in the air, and at this point, there's thrust, so it's being driven up. But at this point, all of a sudden it's going to enter free fall. So we're in free fall now. So the rocket's going like this. And at some point, there's some internal explosion. And that internal explosion, if you've ever used a model rocket, is what makes the parachute go out, what makes everything kind of bust out. But let's say there's no parachute, just so we can ignore air resistance. So we're going to ignore air resistance. But there's an internal explosion which is going to make this rocket just blow up. So all of a sudden, you've got this rocket that was moving in a perfect parabola because there's no air resistance, and all of a sudden it blows up, and one piece goes that way, and one piece goes that way, and one piece goes that way, and there's pieces kind of exploding all over the place. Well, even though there's now a ton of pieces all flying all over the place, the center of mass, because it was an internal explosion, in other words, the net force equaled 0. That means that the center of mass of the system is unaffected by the explosion. Therefore, the center of mass continues on exactly in that same parabola. And that's a pretty interesting kind of thing to sort of wrap your head around. It was moving in a parabola, there was an internal explosion, so the net external force is 0. Pieces are now going all over the place, but the center of mass continues on in a perfect parabola. Okay, so now let's think about having 3 blocks. And these 3 blocks have a center of mass somewhere right in here. So let's just put a little X for the center of mass. And what we're going to do is we're going to say that there's external forces that are acting on each of these blocks. So there's some force here. We'll call that F1 at some angle theta. We've got a force here. We'll call that F2, and another force here. We'll call that F3. And we'll call this one block 1, block 2, block 3. So initially the center of the mass of the whole system is right there. These forces are applied. What will be my acceleration of the center of mass? Well, what we can do is we can think about the x acceleration of the center of mass. So we're looking at the center of mass is simply all of the x components, so that would be F1 cos theta minus F3 over the total mass of the system, so M1 plus M2 plus M3. And that's going to tell me how my center of the mass is accelerating in the x direction. And then AY, same thing, it's just F1 sine theta minus F2 all over the total mass. So M1 plus M2 plus M3. And that will let us figure out how this center of mass is moving, accelerating. And then we can treat these 3 different blocks as one central figure. That helps us measure position a little bit easier. Treating multiple particles as one. Okay, so where are we moving with this? What's this idea all about? What we're developing is an idea of something that's called linear momentum. You've heard momentum before. This is a word that's in our vernacular. But what exactly does it mean in terms of physics? So, linear momentum. Well, we've actually got a preview of it earlier in this lesson. Linear momentum has to do with, and I told you this would be important, linear momentum has to do with how much mass something has and how much velocity it has. In fact, this mv is linear momentum. So we can define linear momentum. And typically we drop the linear, but I'm going to keep it for now. So we just typically we'll just talk about it in terms of momentum, which has the symbol P. So linear momentum equals mv. And the units would be kilograms times meters per second. So let's investigate linear momentum a little bit. First of all, what should be, I think, kind of clear to us is that momentum, as we said, which is mv, well, if we took the derivative of both sides, we'd get dp dt, which is ma. Well, that is super familiar to us, which is that the rate of change of momentum with respect to time equals the net force. So therefore, we get to some kind of important, really important idea, and this is hugely important, which is that without external forces, so we know that if there are no external forces, that the net force equals 0. Well, what that implies then is that dp dt equals 0. All hinged on the edit. We're talking about when there are no external forces. So what that means is as long as there are no external forces, there cannot be any change in momentum, and we'll come back to this again. But what that means is that momentum is conserved. This idea, hugely important. We'll come back to it in a couple days. Well, let's dissect momentum even further. So, we have this expression dp dt equals f net. Well, what if I separated this and we got integrated? So separation of variables, and then we could integrate. So I'd integrate from p initial to p final, integrating from time initial to time final. Well, what I would get on the left-hand side is this is just p final minus p initial, or change in momentum. On the right-hand side, we're going to have to make a little bit of an assumption here for right now. Let's just assume, and we don't always need to do this, but for right now, let's just assume f is a constant. So, therefore, on the right-hand side of this, we would get ft from t initial to t final. And so we get this very important expression, which is that the change in momentum equals f times change in time. In other words, we get a change in momentum when force is applied over some time. Right? So this value here, f delta t, is clearly important. It's what creates a change in momentum. So having some constant force over a change in time, that creates this change in momentum. And because this is such an important idea, momentum is something that we'll be using a lot later on. What creates the change momentum should have its name, its own name. And it does. This is called impulse. And this you've also heard before. This is a term that you've known before. When you think about impulse, you think about something like hitting. Well, again, think about it in terms of, again, you're applying a force over some amount of time. And when you do force over some amount of time, the result is a change in momentum. And this is, again, it's all grounded in the ideas of all the kinematic equations that we've learned before. Let's look at a non-constant force. So let's imagine, we've got some force and time, and our force is changing over time. And if we go from time 1 to time 2, what we know, kind of given our recent understanding, is that this integral, or the area underneath the curve, that area underneath the curve corresponds to J, or impulse. And J is a vector, and the units would be Newton seconds, right? Because once again, it's coming from force times change in time. And the result of this impulse, the result of that impulse is a change in momentum, again, a vector of my system. Okay, so this sums up the main topics right now. So what we looked at, defining impulse, before that defining linear momentum, and before that looking at Newton's second law. So we'll end this video here, and in the next corresponding video, we'll look at some sample problems.